In this video, we're going to use Snell's law in trigonometry to investigate bending light. So let me start by turning on the laser ray. Okay, to begin with, the laser ray is going through air, and then it hits water, and you can see that once it hits the water, it bends. In order to determine the amount of bend, we can use a protractor. In measuring from 0 at the top, we can see that the angle of incidence is about 45 degrees. And then measuring from 0 on the bottom, it appears that the angle of refraction is a little bit more than 30 degrees. So in order to calculate the angle of refraction, we can use something called Snell's law. So let's go ahead and go to our whiteboard and investigate. Snell's law says that n1 times sine of theta 1 is equal to n2 times sine of theta 2, where n1 and n2 are the indices of refraction. Theta 1 is the angle of incidence, and theta 2 is equal to the angle of refraction. So let's go ahead and start labeling our diagram. Theta 1 is our angle of incidence. And in this case, we know that theta 1 is approximately equal to 45 degrees. Our angle of refraction, this angle here, theta 2, and it appears that it's approximately 32 degrees, a little bit more than 30 degrees. But what we want to do is to use Snell's law to calculate that. Over here on the right, we have N1 and N2. Our index of refraction for air is 1. So this is our N1. And our index of refraction for water is 1.333. So this will be our N2. So we just substitute those into the formula. We get N1 is 1. Times the sine of theta 1, which is 45 degrees, is equal to N2, which is 1.333, times the sine of theta sub 2. In order to solve for sine of theta sub 2, we're going to isolate sine theta, and we can do that by dividing both sides by 1.333. So we get the sine of 45 degrees divided by 1.333 is equal to the sine of theta sub 2. In order to solve for theta sub 2, we can take the inverse sine of both sides. So theta sub 2 is equal to the inverse sine of the sine of 45 degrees, which is the square root of 2 over 2, divided by 1.333. And then we can use our calculator to evaluate this. And when we do, we get approximately 32.0 degrees. So the angle of refraction when the angle of incidence is 45 degrees is 32 degrees. And we can go back to the simulation to verify that. If I turn on angles, we can see that the angle of incidence is 45 degrees and the angle of refraction is 32.0 degrees. Now, one question that we might ask ourselves is, what would the angle of incidence have to be in order for the angle of refraction to be exactly 30 degrees? Let's go back to our whiteboard and investigate that question. So our question is, what would the angle of incidence have to be in order for the angle of refraction to be exactly 30 degrees? So in order to answer that question, we'll use the same values for n. So n1 will be 1. Times the sine of we're asking a question about what will the angle of incidence be. So we'll leave that as theta 1. And then equals N2 1.333 times the sine of 30 degrees. Right? Well, 1 times sine of theta 1 is just sine of theta 1. And sine of 30 degrees is 1/2, so we have 1.333 multiplied by 1/2. And then we need to take the inverse sine of both sides. So theta 1 is equal to the inverse sine of 1.333 times 1/2 is 0.6665. And then now we can evaluate that on our calculator, making sure that it's in degree mode. And we come up with about 41.8 degrees. So let's go back to our simulator and see if that works out. We can change the angle of incidence to 41.8. And when we do, we can see that the angle of refraction is 30.0 degrees. So what we've seen is that Snell's law is a useful tool for working with bending light.